Okay, so welcome to everyone to the fourth lecture by Boris. So since she will be not be here tomorrow, I would like to take 30 seconds to thank Julie that she filmed all the lectures in a very professional way and made everything possible. So thank you very much. With a link to your page. Oh, good. So the fourth lecture is by Boris about analysis of random neural nets at large depth.
Right. That's fair. Good job. I'm glad at least somebody has been following the notation, you know. It's always nice. Okay, so thank you for coming back. I'm going to switch gears a little bit today. There's not really going to be I'm lying. As usual, I'm lying a little bit. I was going to say there's not going to be any mean field neural networks here. But actually, secretly, everything will be mean field. I'm just not going to tell you about it. Okay, so setting that aside. So my plan today is to try to tell you about something on how to study neural networks at large depth. So one of the things that people noticed in practice is that at least up to a point, deeper networks perform better in many situations than shallow networks. Like somehow in the 70s and 80s, people used neural networks for various tasks, sometimes with great success. But they tended to use relatively shallow networks, not too many layers. And then they figured out via residual connections and normalization layers and various things that deeper can help you quite a bit in various tasks. So part of my plan today is to try to tell you a little bit about how one thinks about deeper neural networks. And maybe you'll notice that essentially all the results I presented, except maybe the Gaussian process limit, were for one-layer networks, because those are often the easiest to study. Okay, so I'm gonna try to do something slightly harder today in that conceptual sense. Okay, so let me set things up. So let me make some notation. So we're going to consider a neural network just as before. And I'm just reminding you of my notation. So little l is the layer index. And if you want to compute the ith component at layer little l plus 1, corresponding to an input x. Right, so I turned off the biases because I was a bit lazy. So it's the sum over the previous hidden layer, and L. You have to take the weights, WL plus 1 ij. You apply sigma to the pre-activation in the previous layer, evaluated at x. This is the forward propagation equation if you want. This is how we define the neural networks. And we had the following kind of initialization scheme that at least at the start of training, these were Gaussian mean zero variance CW over the width of the previous hidden layer. This is like a kind of CLT scaling. This is at initialization. Okay, so this is the kind of thing that I'm going to study. And little l, just to connect to the title, runs from 1, maybe the way I wrote it, maybe it runs from 0 up to capital L. Okay, so L was the number of layers in the network. Very good. So let me just remind you, because it was so long ago, 2 days ago, I can barely remember what happened yesterday. So what we did in lecture number 2 when we had this NTK or kernel point of view on learning, we found that in this kind of setup, so if we just fix L, and we let the hidden layer widths n1 up to nl go to infinity. So I'm not really writing it here, but we also fix the training data set and the input dimension and the output dimension. We just let the widths of the hidden layers grow. Then we kind of had 2 facts that I sketched for you. So fact number 1 is that at initialization, this stochastic process, x maps to zl plus 1 of x, converges to a Gaussian process that has mean 0, and I called the covariance kernel k capital L plus 1. Okay, and if you are a masochist and you like all the notation, then you'll remember I had this tensor nl plus 1 here. This was just to remind me that each component of the output is actually an IAD copy of the same Gaussian process. Okay, so that's what happened at initialization. And then moreover, we saw that with small step sizes, with small steps, or we did gradient flow, so that was fine. Infinitely small steps. For optimization, for learning, we can replace the fully nonlinear network. Here I'll emphasize the parameters, z of x with parameters theta, by the linearization around initialization. Okay, around theta times 0. So that's why it was called the kernel regime. There's a certain kernel or a linear model that was completely equivalent in the infinite width limit, at least with this kind of parameterization without the mean field stuff for your optimization. And so it was, okay, something mathematically tractable but a little bit sad. Okay, so this was the kernel regime. This is the kernel regime. So the kernel regime is like a mathematical jail, more or less. Okay, it's you put yourself there because you have to take a limit in order to prove a nice theorem, but it's kind of a jail because you'd like to escape. You want to escape the kernel regime. Okay, you'd like to actually describe what real neural networks do, which is, in fact, not the same as linear models. And so there are essentially maybe at least 4 options for how to leave the kernel regime. Okay, so today's lecture is going to be about one of them, going to large depth. But just because I mean to be as expository as possible, let me tell you what kind of things people do to leave the kernel regime and get interesting dynamics, so to speak. So leaving the kernel regime, leaving kernels behind, I'll say. Okay, there are several options. So one we saw last time, right? You can do mean field parameterization. And it seemed kind of benign, but it was actually rather different. Instead of initializing to have an order 1 stochastic process as your output, we scaled down the outputs a lot so that at initialization your predictor was 0, but its gradients were not 0. You get some complicated nonlinear but deterministic evolution for the empirical measures. So that was kind of the mean field parameterization. You kind of change the setup for the model. That's thing number 1. So you can take the data set size, okay, plus the input dimension to infinity. Okay, so you take the width and the data set size to infinity at the same time, and you will no longer be in this kernel regime. Basically, if you remember, but maybe I was too brief about this, when we were studying the kernel regime, what happened was you have to fit a certain amount of training data points that was fixed, and when you were wide enough, you could do it. But the point is how wide you had to be dependent on how many data points you wanted to fit. So as the number of data points grows, you have to change more and more from your initialization to fit them, and this is one way to escape the kernel regime. Yeah?
But in general, the input dimension is given, but it's going to make it float.
Well, but in general, the hidden layer width is also given.
Yeah, it's a choice for you. The dimension is just of data, which are like this.
So you see, but it's just a question of which one is one much bigger than the other? You know, so it's like someone comes to you and they say the input dimension is 5 million. You have 5 million pixels in your image. And your hidden layer width is 5,000. Well, now you're in the regime where you probably should have sent the input dimension to infinity first, and then studied what happened when the hidden layer width went to infinity. So it's like, you know, for a particular realization of a data set and a neural network, you can't tell, like, everything appears large. If I just told you the width is 10,000, you would say, oh, that's big. If I told you the input dimension is 5 million, you would say, oh, that's big. But you know, I want to understand what happens when they're both big. That's kind of what I mean. So of course, I mathematically phrase it as taking the limit, but really I'd like to know non-asymptotically what happens when they're both big and finite size, and they'll interact. There will be some nonlinear effects that come up. Yeah, that's what I mean. Other questions or comments about this? Okay, so this is like thing number 2 that you can do. Relatively little has been done here. We don't actually know how to do this very effectively. So this is a good thing to think about. Okay, the third thing you can do is you can actually take large step sizes, large learning rates. So the NTK regime, the kernel regime, is basically like saying you stay close to your linearization. But you can kind of imagine if at the very first step you take a big jump, okay, you're no longer close to your linearization. And so there are various papers, although not too many, which point out in various settings that if you just have a sufficiently large learning rate, you will no longer be near the kernel regime, even if the data set size is fixed. So it's kind of an interesting, I think, and beautiful thing. And then the large thing, so the next thing is you can take large depth, L going to infinity. Or really, again, when I mean that, I mean both the width and the depth can be large. So, and that's mainly what I'm going to try to discuss today. But this is like a non-exhaustive list of the things you can do to leave the kernel regime. Basically, anything you change will take you out of the kernel regime. That's kind of the message. And so these are interesting things to study as a result. Okay, so let me just pause for 1 second and ask if there are questions or comments about this. Is this okay?
Where's the optimization procedure involved in all this? Can you remind me?
So yes, I didn't write it down, but if you want, it's right here. D by dt of theta of t is minus the step size times the gradient with respect to theta of your loss. So maybe I should put a box around it and say that's the kind of thing that I imagine that we were considering.
One thing that I wondered is does it make sense that T is already attaining, let's say it's attaining equilibrium, that's another, because you want T to infinity, basically, right? So that we can get the optimal.
Yeah.
So that destroys the initialization, the random initialization.
No. No, I mean, where you start impacts very much where you end up because it's not a convex type problem. It's not as if there's a unique minimizer for your loss. That was kind of the point. There are many minimizers, and so where I started influences where I end up. You don't totally forget the initialization for that reason. Yeah.
Maybe I can ask a question that is, well, related probably to everything you said before. So if we, apart from this case which you described in lecture 2,
Yes.
where it was clear, so exactly what you were going to,
Yes.
right? This is clear. When we obtain, so whatever you do out of the sleep, or whatever you do today, whatever you did yesterday,
Yes.
you obtain some limiting results. You obtain some equations, some differential equations.
Yes.
Quantity. What can you see from it? Can you see something? Because
Yes.
for linearization sake, we could see something, right?
Yes.
What is it?
So let me give you some examples of things you can hope to say. So thing number one you can hope to say is you can hope to then say that I mentioned this, but I'm going to start with it. You found a good way to initialize and to set your learning rates and everything and to scale them together with the scale of your model. So if you remember, for example, in the mean field initialization, I didn't emphasize it, but it was important to have the width of the model as a prefactor in the learning rate. And so this tells you that that's the units in which you should be searching for your learning rate, for example. So there's some kind of practical questions of how to parameterize the model. That's thing number one you learn. So thing number two you learn is once you have a description of the training dynamics, especially if you can do it where you can take the data set size to be large, you can then ask, well, what statistics of your data generating process are being learned and in what sense? You know, you could say, okay, the first layer weights, the way they change throughout training, I'm not saying this is what happens, this is like an example, you know, is they get a low rank perturbation that comes from the like top eigenvectors of the data-data covariance. You know, like something human computable about what it is about my data generating process that I'm learning through my sample of training data and how it gets encoded into the network. So then I can understand what features of the data generating process I'm using, what aspects of it to make predictions on new data points. That's a thing you could hope to learn, but it depends on how complicated your limiting description is. You know, when your limiting description is complicated nonlinear PDEs, maybe you can say something and maybe you can't. Depends on whether you can analyze those equations in some more or less direct manner. But a thing that I will advocate today when I tell you what I'm going to do, I'm basically going to study these random neural networks just at initialization, try to understand what happens when the depth is large, is, you see, initialization is more interesting than it might seem. It's not just about what happens literally before you do any training, because any finite number of steps around training that you want to analyze, you could just tailor, expand, and write as something about initialization. So if you want to know what the gradient looks like after 0 steps, like how your first step of optimization looks, that's just a question about initialization. If you want to know how your Hessian looks or how much your gradient changed after a step, still you can just write it as something at initialization. Ultimately, they're all integrals at t equals 0. And so you can basically hope to understand early time training dynamics, essentially no matter how complicated your limiting description of dynamics is, because you can just tailor expand to your heart's content in your time variable.
Is it also not ultimate goal to say, okay, despite the fact that we have a lot of minima where we can start potentially. Well, in this particular setting, we actually don't stack and converge pretty fast to the true parameter.
So okay, it's true. You do want to say that, but for me, I've so much internalized that I'm always going to fit any data you give me that I don't even view that as a surprising consequence. I just think of that as like, of course, that's going to be true. But you're right. But moreover, like maybe I should also say one thing you can learn from the dynamics, at least in some cases, is you can have some very concrete descriptions. Like the first thing you learn is the rank 1 approximation to like your data generating process. Then you learn the rank 2 approximation. You can say something very qualitative about how the optimization trajectory works, and it explains how neural networks are searching through all possible ways of fitting the data, and why in some sense they find the simplest way of fitting the data. You know that. So you can't do that for completely general setups. That's too much to hope for, at least with current technology. But in some cases you can really get that granular of a description. You know, you first learn the degree 1 polynomial approximation, the degree 2 polynomials, and so on and so forth. So there are some papers that really can bring that out for you. Yeah.
In today's lecture, is it correct to think about the equivalence between theta and the weight W?
Yeah, so theta is just a vector that has all the W's in it.
Right, then you mentioned the Hessian. Let's say if you want to look at the second order surface approximation, that if you have thousands of weights, it will be a huge matrix, right?
Yeah, for me, I just write it as H. You know, I'm saying like theoretically it's just a matrix. Now realizing it on a computer may be painful, but you know.
In practice, the approximate hashes and approximate weights.
Sure. I'm not saying I'm going to use it for an algorithm. I'm just saying if I want to understand something about learning, I might want to say something about the spectrum of the Hessian as you train. And if I can just give you a theorem about it, you never had to calculate it unless you don't believe me. Then it's your problem. You know, okay. Okay, very good. So good? All right. So let me just say, so today, my goal is to explain how to think about random neural networks, i.e. at initializations, when both the hidden layer widths and the L can be large but finite. So really how to understand the joint effects of depth and width. And what I'm going to try to convince you of is that you cannot understand the finite width effects without understanding the large depth effects. They're basically the same thing. That's going to be like the TLDR of what I want to say. So let me try to like write the takeaway here, what the main message is, and then I will try to illustrate it in a variety of senses. Okay, so here we go. So after taking CW correctly, so remember that I didn't write it down here. Maybe I should have. Maybe I will in a minute. But not only did we have this description as a Gaussian process in the limit, we had a recursion for the covariance kernel after L plus 1 layer in terms of the covariance kernel after L layers. There's some formula for it. And that recursion depended on this constant CW, the variance of the weights, and the nonlinearity that we had. Those are kind of the two things in the problem. And so if you choose this CW correctly, and I'll explain what that means, at large L, okay, and finite width and all of this, the stochastic process that we're interested in, this function of theta at initialization, I'll from now on basically just drop the thetas, is determined by the following. So you might have thought that this is the way people usually talk about it. The capital L is some measure of complexity of your neural network. It's like the depth of the network. The deeper you are, the more complicated a function you get. You might have thought that, but you would have been wrong. And in part, you already know that you're wrong because you know you just get a linear function in the infinite width limit. So you can't really capture the complexity of a neural network just by thinking about the depth. And really what you should think about is what I call the effective depth. So the effective depth or complexity effective depth of the network is the ratio between L and N, which more precisely is just the sum of the reciprocals of the hidden layer widths. Okay, so it's essentially the statistics of this field are determined by this notion of effective depth. Okay, and let me finish the sentence and then I'll stop and try to explain. But it determines many of the properties, essentially all the properties of the neural network that you're interested in near the start of training. So it determines, for instance, how close you are to being a Gaussian process. So I told you in the second lecture that you converge to a Gaussian process. But you might ask, how close are you, in fact, to being a Gaussian process? And I will explain today that, at least in one sense, the distance to a Gaussian process goes to 0 as n goes to infinity. That was the result from before. But really, it goes to 0 like L over n. So if L and n are both big, you may not be close to the Gaussian process at all. Okay, it also measures the correlations between neurons. So remember, part of this result, or the Gaussian process limit, is that all the neurons are independent of each other. That's the distribution you get. But okay, that's not true at finite width. And the amount of correlation you have is, again, going to go to 0 at infinite n if you fix the depth, but actually scales like L over n. Okay, it also determines the distance to a linear model, to the linearization. So if you want to ask, how close am I to the NTK regime? How close am I to step number 2 being true? Well, okay, I told you that at fixed depth, if you send the widths to infinity, this is true. That's a theorem. I didn't lie to you. But actually, if you're at finite width, as long as the depth is pretty big, you may not be close to the linearization. So the depth pushes you away from this kind of kernel regime. Okay, it determines other things too. Things like stability of your gradients. Stability of gradients. Okay, let me not belabor that too much. Let me just say ... Okay, so my main message in some sense, if you hear nothing else, is that there's like a new, if you want to use some fancy words, thermodynamic variable. When both the depth and the width are allowed to be large, the right way to summarize the depth or complexity of the model, how different it is from a linear model in a variety of senses, is not the depth separately or 1 over the width separately. It's really their ratio. That's basically my claim. Yeah.
How do you think effective?
Well, so because, for me, these 2 points here are the statement that if you fix the number of layers, if the width go to infinity, you become a linear model. A linear model for me is a depth of 0 neural network. There's no nonlinearity whatsoever. And what I'm saying is if L over n goes to 0, you will still be a linear model. That's all I mean. And so, and then beyond that, okay, I worked with some physicists and they have fancy ways of naming things. So it's like the effective amount of nonlinearity that you have. It's how different you are from your linearization. So it's something like, okay. So it's just to be memorable. That's the short answer. Yeah. So is there another question? Yeah, please.
Just a terminology question. How would you call the first equation on the first board? How would you call the left-hand side? You would call it the input to the L plus, the neuron in the L plus 1 layer?
So this is neuron number I
neuron
in layer L plus 1. So people usually call it the pre-activation of neuron I in layer L plus 1. Pre-activation is the thing you feed into sigma. Yeah.
Now, is there a reason why you always discard the intercepts, the biases?
Only because I'm lazy to write. Everything I say can be done with the biases too.
They affect nothing. No rates. They don't affect anything.
No, not on this level of analysis. No. Right. Everything's become a little longer. There's more notation. There's plenty of notation as it is, I think. So yeah, but it's fair. I should have emphasized that. Other questions or comments? Okay. Oh yes, please.
The bias is the weight of the constant, so as long as you have a constant in your model, that should be equivalent, full equivalent, right?
The short answer is yes. The slightly longer answer is it depends. Depends what you mean by equivalent. But no, you're right. Yeah. I'm not emphasizing it, not because I'm hiding something in this case. Okay, very good. Very good. So here's my plan. I'm not going to directly state the theorem I hope to sketch the proof of. That's going to be the last bit, because it might be a little bit painful, or you might love it because it's painful, one of the two. So I want to try to convince you, though, at a very high level, and use this excuse to connect to what I think are really beautiful problems in random matrix theory. Why L over n? Like, I'm basically claiming that the right way to understand a neural network is through this ratio of L over n. But like, you could say, that sounds crazy. Why would that come up? At least you should have a reason for me, and I do have a reason for you, or something that might suffice as a reason. So I have in my notes a section about why L over n. Why not something else? Okay, so here I'm going to take perhaps the simplest kind of neural network. So I'm going to take a neural network in which the nonlinearity is the identity, so there are no sigmas whatsoever. Okay, I'm going to take CW to be 1, so I'm going to study everything only at initialization. So I just have, big matrices with standard Gaussian entries, or 1 over n Gaussian entries. All the NLs are the same value, n, and I'm going to fix an input of size 1. Okay. So what in the world do I have? So I just have a neural network that looks like this. ZL plus 1 of x is just a product of matrices times x, like that. And okay. So in the way I've done it, every width, the input dimension, and the final hidden layer width and everything are n. So that's the way I've set it up. And I want to just point out that, okay, this is an extremely special case of studying random neural networks. But people have been studying products of random matrices forever. And there are like plus infinity papers written on this particular subject, in the sense that you'll never hope to read all of them. So there may as well be plus infinity papers. Okay, and I think a good way to think about these random matrix products is kind of in the language of dynamical systems. So I put L on the x-axis and n on the y-axis. And I think of L as being a time parameter. I sort of mentioned this, I think, in the first lecture. But this is like a way people study Lyapunov exponents of chaotic dynamical systems. You say I have a very chaotic dynamical system, and my time 1 evolution is multiplied by an independent random matrix. That's like a simple mathematical object for such a thing. So in this dictionary, L is a time parameter, and n is like the number of degrees of freedom, or just kind of the dimension of the system. Okay, and already when you do this kind of picture, you know that L and n are going to fight each other. Right? The bigger the system, the more degrees of freedom, the longer it's going to take to come to equilibrium. So there's going to be some tension between n and L. And okay, if you're a probabilist or a mathematical physicist or whatever, you probably know that there are kind of 2 main regimes where people study these questions about such matrix products. One is you fix the number of terms in the matrix product and you let the matrix size go to infinity. This is what the probabilists might call a free probability regime. Okay, I call it the NTK regime. Okay, but now you know why. Fine, and so this is, a big, beautiful subject. It's all about maximum entropy distributions for the singular values or the eigenvalues. And okay, so let me not belabor that point. So that's beautiful and interesting, and I think doesn't need too much motivation. But there's an equally well-studied other regime, which is the opposite. You fix the size of the matrices, and you let the number of terms in the matrix product go to infinity. Okay, this is like the world of the multiplicative ergodic theorem and the study of things like Lyapunov exponents for dynamical systems and whatever. Okay, and these 2 regimes couldn't be more different from each other. The techniques, the results, everything is completely different. And the basic point that I'm trying to make is that the limit as n goes to infinity and the limit as L goes to infinity don't commute. That's like the mathematical issue. That's why you can't understand what happens at large depth by going to large width first. And I want to show you what happens over here. There's only like order of 10 papers written over here, and I probably wrote 3 of them. Okay, so it's a very young subject. And so even on this random matrix side, we understand very little of what happens in the middle. But there's one calculation I can do for you on the board, which I'm going to do right now. Okay, so I'm going to show you on the board that these 2 limits don't commute by studying the simplest possible observable. Okay, you just fix an input x of unit norm, and I ask, well, what's the size of the output? Okay, so that sounds innocent enough, but hiding beneath this innocence is a deep, dark beast. Okay, so let's do this together. So let's fix the number of terms in the matrix product and take the width to infinity. Okay, so maybe one of the students who doesn't already know the answer can tell me. So I claim that this random variable converges to something. What does it converge to? Okay. Say again?
Brownian bridge?
No. So I have a fixed x, and I just hit it by a product of matrices. So this is a random vector in Rn. And I take its norm. So I'm just supposed to get a scalar random variable.
Some chi-square, we hit like some sort of, so it's a...
So if I had one matrix, it would be exactly a chi-square, or square root of a chi-square maybe.
If the w's were all identity, then this would just be the norm of x.
That's right.
And if the norm, if x was itself...
okay, but x has norm 1. So what have we gotten 1? But the W's are not the identity, so what am I supposed to do? So they're not the identity, but maybe they're kind of like the identity. Okay, so there's a basic theorem, right, which says if you have an n by n matrix with IID Gaussian entries, mean 0, variance 1 over n, then it's very close to being in isometry. On any finite dimensional subspace, it preserves lengths and angles, or approximately does so finite size and does so asymptotically. You only have finitely many such matrices here. And so you're just going to get exactly the norm of x to pop out. So actually your intuition was great. Okay, so here you get 1 almost surely. Okay, beautiful. That's good. So now let's do the opposite thing, just because it would be a very asymmetric picture otherwise. So let's fix the number of, or the size of the matrices, let the number of terms in the product go to infinity. Now what do you get? So maybe this one's a little harder to see. We're actually going to prove this in just a moment. So here's the basic idea. If you take a product of L plus 1 matrices, and you want the singular values to remain order 1, the natural thing to do, and indeed the thing you're supposed to do, is raise it to the 1 over L plus 1 power. You have a product of a bunch of stuff, you have to kind of normalize it, take the geometric mean. So after this kind of normalization, what it turns out is the singular values are asymptotically between 0 and 1. You have to, either you know that or you don't, but it's true. Okay, but that's after this kind of normalization. So without this normalization, all the singular values go to 0, because you're raising these small numbers to the power L plus 1. Okay, so here you just get 0 almost surely. Okay, well you see that the two limits don't commute. Okay.
This is easy to see in dimension 1.
Yes, it's easy.
We have IID classification.
So, but actually it's easy to see in any dimension, as I'm about to show you. In the Gaussian case, there's a trick. Okay, there's a trick that it's going to combine your two tricks. Yes, please?
Just one question for Mugan. The sigma identity is key for all of the results that are available for the moment.
So for these random matrix products, they come up when sigma is the identity.
But there are, the same question makes sense for any, the sigma that you presented in the first class, let's say. So the question still remains, is it open? Is it open?
So for ReLU, you can do this question exactly. For the ReLU nonlinearity, you can do this exactly. And for other nonlinearities, I'll state a theorem in a moment. So, but yeah, some stuff is known, some stuff isn't. But okay, yes?
Okay, so this is sort of a technical question. Technical because, so the fact that the two limits don't commute, okay, it's very interesting mathematics.
Yes.
But you can make both n and L get large at the same time by making one a function of the other. So you don't. So they don't commute, but you don't have to take the limit independently. Like this happens all the time. At least, for example, when you're doing non-parametric regression, right? So like kernel regression, not the kernel in this sense, but the kernel in the Nadaraya-Watson sense, right? You want to figure out what happens to the regression estimator as the sample size increases and the bandwidth goes to 0. So you don't let the bandwidth and the sample size, you don't let n go to infinity and the bandwidth go to 0 independently.
So we're about to do the same thing right now. The question is, how do you scale the depth and width together? How do they come up? And the answer, of course, is going to be you should scale them linearly if you want to get an interesting answer.
But why is it an interesting mathematical question to say that the limits don't commute?
No, that's how you know that you have to study when both of them are large. What I'm saying is if you want to understand what happens when L goes to infinity, you cannot first take n to infinity and then ask what happens at large L.
You get misleading.
You're just going to get the wrong answer. And so if you really want to know the answer, you know that you can't do that. It's exactly what you're saying. And you have to scale the two of them together and ask what happens as they both grow. So we're about to see that come out organically in this simple case. But it's exactly the point, indeed. It's just harder to do it for nonlinear networks. Okay, so let's do it. I'm going to show you a calculation. So we're going to calculate this object. People who've seen me give this talk are going to be bored, but that's okay. I find it exciting every time, personally. So, okay. Easily excitable. Okay, so we need to calculate the distribution. I claim there's a non-asymptotic formula for the exact distribution of this object. Okay, so let's do it. So what am I going to do? I'm going to channel my inner Mark. It looks like a product of things. I'd like to put them in the exponent. Well, it's not quite so simple because matrices don't commute in this way. But maybe they do. Maybe they do. Let's see. Let's see. So let's try. I'm going to do my best to be Mark, but I can only do what I can do, which is to just take out the first size of this first vector you get. So that was moderately successful. And now what do I know? Well, so remember the W's are Gaussian matrices. So this right here is just the norm of a standard Gaussian vector. Right? It's a unit vector times a standard Gaussian matrix, okay, with the 1 over n in front. So this is nothing more than a chi-squared distribution with n degrees of freedom with a 1 over n due to the variance. Okay, I have to take the square root. Oh, God. Because I haven't taken the square of the length of this vector. So I know the distribution of this object. But moreover, this W1 times x is a standard Gaussian vector. It's rotationally invariant. Its norm is independent of the direction. So this is just some other unit vector. I'm just going to call it x again, because I have terrible notational skills. Okay, it doesn't matter. This matrix W2 is rotationally invariant. It doesn't matter which x you chose. So now you just run this argument again, but you have one less matrix in your product. Okay, so in the end, this is the sense in which I can kind of do your one-dimensional trick. You get in distribution that this is the product, on L goes from 1 up to L plus 1, of a bunch of independent chi-squared random variables that are appropriately scaled with a square root. So that's the sense in which the chi-squareds come up. Okay, so that's a beautiful thing. And you can see the fight between n and L occurring. Okay, they're like the matador and the bull, more or less. I don't know which one's which, honestly. Not a great analogy, maybe. But as n grows, each of these chi-squared random variables tries to concentrate around its mean, which is 1. Right? And that's why you get 1 in the free probability limit. The n wins in this result. Maybe we'll say that's the matador. Okay? But as L grows, each of these things has a fluctuation around its mean. And the more terms you have in the product, the more the fluctuations get accentuated. So this is like the bull. The bull tries to drive you away from the situation where you get the mean. So let me make this a bit more explicit. Let me write it as x sum log. So this is x of 1/2 the sum on L goes from 1 up to L of these random variables, which are the logs of independent scaled chi-squared things. Okay, it's much clearer to see in the exponent what happens. So the mean of each one of these ID random variables is on the order of 1 over n, and so is its variance. And so when you apply the CLT, if L is large, so this is applying the CLT in the exponent, you should just trust me. I did the algebra right. You get a Gaussian with mean minus L over 4n and variance L over n. Actually, L over 4n, the way I've normalized it here. Okay, so because each of these terms contributed 1 over n to the mean, and each one of them contributed 1 over n to the variance, and there's L of them. That's how it works out. And so this is why L over n comes up. See, the L over n is basically saying each layer is 1 over n away from the Gaussian process limit. But when you have L of them, the corrections add up. And they add up in the exponent in this way. And so what you see is that if you want to interpolate between these two regimes, you have to introduce a new variable. This is this non-parametric thing, right, where you have to track, you have to let L and n grow to infinity together. L over n is, let's say, a constant beta. You go off to infinity in this way. And so this regime up here is characterized by beta equals 0, where n is much bigger than L. This regime here, beta equals infinity. And in the middle, I basically get e to a Gaussian with mean minus beta over 4 and variance beta over 4. And now this thing, now you get a nice way of interpolating between the two regimes. Right? When beta is 0, you get e to a Gaussian with mean 0, variance 0, which is 1. That's good. I didn't mess it up. And here you get e to a Gaussian with mean minus infinity, okay, and standard deviation square root of infinity. So you get 0 almost surely. Okay, so this answers how to scale L and n together. A priori, maybe L should have been a polynomial in n or a log in n, but this kind of tells you the answer. Okay, and this is really the simplest example of how kind of to think about L over n appearing. Something more complicated, but ultimately similar is going to happen for nonlinear networks as well. Okay, so let me just stop here for one moment and see if there are comments or questions about this. And then I'm going to try to move back to saying something about neural networks. Yeah, please. So, okay, so I know about 2 kinds of results. Well, that's not true. I know about many kinds of results, but let me tell you about 2 of them. So result number 1 is you might ask about the entire spectrum of this matrix product. Here, like, you could ask about all the singular values. Here I just took a linear statistic, essentially. So for the spectrum, if you take the singular values, you raise them to the 1 over L power, you take n and L to infinity, I can tell you what happens to the spectrum over here. Only to the global distribution of the spectrum, only for Gaussian matrix products. Don't know how to do anything else. And then if you didn't have Gaussian weights, this funny trick used the rotational invariance of the Gaussian. I can still prove to you a universality result. You always get this distribution regardless of which weights you had. You just have to match a couple of moments, like 0, 1, 2 moment, have some finite higher moments. So there's some assumptions, but you have a standard kind of universality result for this particular, yeah. Any questions or comments? I'm going to erase this while people think. Let me say there's a lot of, I think, beautiful open questions on the random matrix side here. Yeah. Okay, very good. So let me now try to move towards the neural network side and tell you the simplest place that I know of for genuinely nonlinear networks where L over N appears. And I'm going to try to explain why, in a sense, it controls the distance to the Gaussian process limit and controls the correlations between the neurons. And I'm not going to make any comments about anything else unless I'm forced to. I don't know how that would happen, but maybe it could. OK, so to do that, let me make some definitions. I'm going to... Yes.
The L over N allows for one, some of the, none of these results allow for some of the ends to be controlled.
Yeah, but by L over N, I just always mean the sum of the reciprocals. I just don't want to write it.
But this covers like the case where some of the ends are remaining, let's say 10, and the other guys are the ones that are doing all of the.
So the short answer is no. They all have to be large for me. They all have to go off to infinity. And it's kind of like in random matrix theory, if you have a 7 by 7 matrix, what are you going to tell me about it? Not much. You know, like n could be finite, but it has to be kind of large because your error terms will look like 1 over n. And if n is 7, you don't have any kind of control on the error. Yeah.
Even if the other dimensions are going up.
Correct. Correct. You need all of them for these results to grow. Right. OK, so let me make a definition, or really remind you of a definition, which I suspect you've seen, given that many of you talk to Giovanni. Giovanni is the world expert on things like this. OK, so you know, I'm trying to understand, like I've kept this up for a reason. So if I just fix the depth and the width goes to infinity, you get a Gaussian process. Now I want to ask what happens when n is large but finite. I want to do kind of perturbation theory around this limiting regime. And so I need some mathematical language to talk about things that are close to Gaussian but not exactly Gaussian. Okay, and so there's a variety of things you can do, but I choose to use cumulants. So I'm going to remind you what cumulants are, and I'm going to use them to describe how close I am to a Gaussian. Okay, so here's the definition. So if x is a scalar random variable, then if you take the log of the moment generating function, okay, just viewed as a formal power series, so it's a random variable that has all moments finite, let's say, though I don't really care. And you just Taylor expand it as a power series in t, in your formal variable. These coefficients that appear, this kth coefficient is called the kth cumulant of x. Okay, that's the definition. Okay, you can either love it or hate it, but that's what it is. Okay, very good. So from our point of view, a thing to notice is the following. So note that x is Gaussian, mean 0, variance sigma squared. And remember, the moment generating function of a Gaussian is just e to a quadratic polynomial. Right? If and only if kappa k of x is equal to 0 for all k greater than or equal to 3. Okay, that's like a basic observation. So if you want to say that something is close to Gaussian, one thing you could do is you could measure, well, how big are the cumulants starting from the third one? Okay, and if they're small, then you're close to a Gaussian. And then if you know a lot of interesting things like Stein's method and Malyavand calculus, which I don't really know, but Giovanni knows, so you can ask him. You know, Ivan knows too. I know both of you know. You can turn estimates of cumulates into estimates on the distance to a Gaussian in various senses. Okay, but like this is the basic point of view I'm taking. And so in order to study what happens to my neural network to compute non-Gaussian corrections, I'm going to study the cumulants of the output. Okay, so the basic object I want to study is the following. So here's my definition of the object. I'm going to call it kappa L sub 4 of x. Okay, and my definition is it's going to be 1/3 of the fourth cumulant of the random variable I get by just studying one of the neurons in layer L evaluated at x. Okay, so the bullet point number 1 from lecture 2, this convergence to the Gaussian process limit. So the third cumulant is 0 by symmetry. Okay, this is the first one that has a hope of being non-zero. So basically, this thing goes to 0 as n goes to infinity. And in some sense, it's the first measure of how close am I to being a Gaussian. Okay, so that's what I'm going to focus on right now. The things I tell you about can be extended to all the cumulants, but it's only more painful. Okay, and so you'll see in just a moment why I care about this 1/3, but for now it's just a definition. Now let me tell you two equivalent definitions of this cumulant, which you can work out by just some manipulations of the definition, but I won't ask you to do it, of course. Okay, so one thing is you can write it like this. This is 1/3 of the expectation of this random variable to the fourth power minus 3 times the expectation of this random variable squared. Okay, squared, like this. So this is just to reflect the fact that if z were actually Gaussian, this would be 0, right? The fourth moment of a Gaussian is 3 times its second moment squared. That's like a basic formula. So that's one way you can interpret this cumulant, and this is going to be like this distance to the Gaussian process kind of thing. How far am I away from looking Gaussian? But it turns out for neural networks, there's one more kind of clever and I think kind of nice way of thinking about this thing. It's also the covariance between what happens in neuron 1, let's say at layer L squared, and what happens at neuron 2 in layer L squared. Covariance between these two random variables. So you see again, in the infinite width limit, what happens is any two neurons in your same layer are independent of each other. So the covariance goes to 0. But what's going to happen is at finite width, they're not independent. And this fourth cumulant simultaneously measures the distance to Gaussianity and something about the correlations between different neurons. It's just a kind of convenient device for doing both these things. Okay, so I'm going to erase over here. And then you can kind of ask me questions and make comments about this definition before I state a theorem and try to tell you a little bit about how to actually understand the cumulants of a random neural network. Is this okay?
So there's no difference between the two terms in the covariance?
So this is the first neuron and this is the second neuron. So yeah, so it's like how correlated are different neurons in the same layer. And the other one is how non-Gaussian a single one is, and it just so happens that for neural networks, these two are the same. It's just maybe I do some more erasing. I see people puzzling it out, so I may as well use this chance. Oh yeah, doing well. A lot of time. I always say that.
Okay, you probably say it, but in general, analyzing the false cumulant is not sufficient. Like when Gaussian spaces, you can have arguments.
So the theorem I'm about to present in the paper does all cumulants. Okay, so I just want to explain the simplest case I possibly can, and the other ones are just more painful. Yeah, indeed. But like for me, I'm mainly interested in situations where you're far from being Gaussian in a sense, and so you need all of them. But like this is a start. If you can't do this, there's no hope for you. Yeah, indeed. Okay, very good. What? Say again?
What's the interpretation of the fact that you have the last like identity, the covariance equals regardless of that.
I mean, it's just the idea that if you think about it, you know, a neuron in layer L is just a Gaussian linear combination of the whole vector at the previous layer. And so that's true for all neurons. So when you just condition on the previous layer and calculate these, either this covariance or this expectation, you get the same kind of thing. And the 1/3 comes from the fact that, you know, the third Gaussian moment of the weights in that layer is 3, 4, you know, whatever. Yeah, it just is what it is. I'm not sure what else to say about it. Yeah. Okay. So here's the theorem I'd like to prove. I'm not really going to prove it, like most things I do, but I'm going to give you an idea of how it goes. So first of all, so remember that one of the really interesting things, I keep stressing it partly for this reason, about this Gaussian process picture for the infinite width neural networks is there was a recursion that described the kernel after L+1 layers in terms of the kernel after L layers. That was like a mechanism that allowed us to say something interesting, maybe. And so what we're going to find is there are actually recursions that describe all the cumulants as well, from one layer to the previous one. So we have the following recursion, for instance, on the fourth cumulant, although you can in principle write them down in every layer you want. So you get CW squared divided by NL+1. Then you get NL or NL+1. Let me see, NL+1. Then you get the variance with respect to your Gaussian process at the previous layer of the square of the nonlinearity evaluated at one of the neurons. Okay, plus you get CW over 2, see if I get this right, times the expectation with respect to the infinite width Gaussian process thing, the second derivative of your nonlinearity evaluated at one of these pre-activations in the previous layer, squared times kappa L4 of x, plus a correction, which is O of n to the minus 2. Okay, so let me just like orient myself for a second about what in the world this is supposed to mean. So the way I think of it is I think of this like a hierarchy that comes up in mathematical physics or wherever it comes up. You first have to understand what the covariance kernel does at infinite width. So in my mind, I have this recursion for the covariance kernel. I understand something about it. And now I think of that as an input. And I'm saying, if you want to know the fourth cumulant at layer L+1, the only thing you have to know is something about the kernel at layer L, which I already know. Now there's a 1 over n in front of this kind of source term in the recursion. And then there's some coefficient which knows about the kernel at the previous layer, this infinite width Gaussian process kernel, the fourth cumulant at the previous layer, and then higher order corrections. Okay, that's how this recursion is structured. And let me just say, this thing has an interpretation. This turns out to be the derivative, maybe I'll write the derivative this way, of the kernel at layer L+1 evaluated at x with respect to the kernel at layer L evaluated at x. So the thing inside of the square. That whole thing has this kind of interpretation. Okay, so it's saying that how much the fourth cumulant moves is related to how much the kernel moves between layers. So it's some kind of natural object that comes up. Okay, and when I wrote at the top, I was careful to write it, after taking CW correctly, okay, that was good. Taking CW correctly means making this term approximately equal to 1. You don't want the Gaussian process kernel to be moving too quickly as you change the depth of the network. It's like tuning your dynamical system to a critical point. That's at least how I think the physicists would think about it. Okay, and so if you just imagine for a second, so this is sometimes called criticality, tuning to criticality. So if just the form of this recursion is very simple. Okay, so at criticality, if you just allow me to set this coefficient exactly equal to 1, what do I get? I get kappa L+1 for of x is equal to, well, it just looks like this. I'm going to shorten it. It's some constant which depends on only this KL, but this KL isn't really changing. So just some constant divided by n plus kappa L for the previous layer plus higher order corrections. That's what it looks like. And so what you see is, just like in the linear random matrix story where you had the product of matrices, each layer gives you a correction of order 1 over n, but you have to sum up over L layers. Okay, so in general, what you find is that there's a constant that depends on sigma divided by, sorry, I'll write it this way, times L over n, little l over n, plus higher order corrections, where these constants here I don't control. They can depend on the depth and the nonlinearity in arbitrary ways, at least for the purposes of this analysis. Okay, so this is the kind of theorem you can get recursions for cumulants at layer L in terms of cumulants of either the same order or strictly smaller order at the previous layers. Okay, that's what it makes it a kind of a hierarchy. And you can solve these recursions and understand that although the cumulants were 1 over n suppressed, they actually grew with L. So this is like what physicists might call a marginally relevant perturbation. Not that it matters very much. Okay, so let me write down one more thing I'd like to check as part of this theorem, and then I will try to sketch the proof for you. Okay, so let me write it down and also take comments and questions and things. So moreover, if you allow me one more piece of notation, let me write GL for the finite width variance. So it's just the actual variance of neurons at layer L, but without taking n to infinity. Okay, so GL converges to KL as n goes to infinity, but this is the actual variance of my neurons at finite width. Then I get the following kind of formula, which I think is kind of beautiful in its own way. Okay, so if you ask me to compute the expectation of any function of some finite number of neurons at layer L plus 1, okay, I goes from 1 up to m. Well, what I know is that as n goes to infinity, this is just as if the neurons were independent Gaussian. But I'm interested in the corrections to that formula, and you can write the corrections out explicitly. Okay, so you get the expectation of f with respect to this g, which just means you treat all the neurons as IID-centered Gaussians, but you have to take the finite width covariance, or the finite width variance, because I'm only doing one input here. And then there's a correction which looks like this. You have kappa L plus 1 4 of x over 8, okay, believe it or not, but that's what it is. And then an expectation again with respect to this Gaussian measure, but there's what the physicists would call an insertion operator, or like a deformation of your observable. And you have to do this. You take the sum on I goes from 1 up to m of the second derivative with respect to these parameter variables that you have. This is like the Laplacian in the variable z. You square it, you apply it to f. Okay, and then you have corrections of higher order. Okay, so this for me is like, in fact, let me put the k here. It's just fine, it turns out, because this object's already at order 1 over n. So this for me is like the dream. Okay, a dream. I have many dreams. Let's be serious. So the a dream in the sense that I want to know how to compute expectations of some function. That's really what I want out of life. And the only thing I really know how to do is Gaussian integrals. Let's be serious. And so what I'm saying is, in order to be able to compute the expectation of some function and know what the finite width corrections are, I only have to be able to compute some Gaussian integrals. Okay, so you write everything as being integrals basically against the infinite width Gaussian limit, which is relatively simple-minded. But you see that there's this kind of interesting correction that you pick up, which has to do with the Laplacian and the variables that you're interested in. Okay, so I'm going to derive this formula for you. The hardest thing about the formula is writing it, believe it or not. That's not true, but yeah.
So GN is that expectation?
Yeah, so G, yes.
Yeah, what do you mean as expectation with?
So, sorry, so when I write the KL here, this means with respect to the infinite width Gaussian process. And here, this means also all the neurons are independent centered Gaussians, but their variance is GL rather than KL. So you have to take the variance that you have at finite width, because the variance at infinite width has a 1 over n correction to it. And because I only throw away terms at 1 over n squared.
So GN is the variance for finite n.
Yeah, exactly, precisely. So I should say this is KL plus order 1 over n corrections. But this order 1 over n correction is actually important in general, because it gives a 1 over n correction to this f integral, and I only throw away terms that are 1 over n squared. So I'm being careful. I could have lied to you, and probably nobody would have noticed, but I would have felt bad. I would have felt fine, actually. That was a lie, but okay. Yes, please.
And where's the n? The n is in the...
So the n is in the k. It's in the K. So you see this recursion right away shows that K is an order 1 over n object. K4.
And would it be possible to isolate it as explicitly n times constant?
Yeah, I just did.
Oh, sorry.
Yeah, I did, correct. I just prefer to write it this way because it looks nice. But indeed. So you have to track through it, but the fourth cumulant goes to 0 at infinite width, but it goes to 0 like 1 over n, and that's the only thing that deforms your expectations at leading order. That's kind of how it works. Okay. So I'm going to do some erasing and let people digest a bit, because I want to show you something about the proof. But maybe you'll wave me off and tell me that nobody wants to see the proof, and then maybe I'll tell you some jokes instead or something like that. You know, please.
Sorry, just a question to prove. So, at L plus first step, the cumulant, you get this formula at first count.
Yes.
So now I'm just trying to say, so you start at when L is 0.
When L is 0, you have 0.
You have 0, right?
Yes.
But at each further step, you pick up an error for the 1 over n.
Yes. And so you add up L of them, and you get an L over n correction. So,
Yeah, but L over n, if L, capital L, has the same order as n, this is not goes to 0.
well, indeed. So you see, that's why I was sneaky, or maybe you'll say careful. So in here, in this thing, the errors depend on capital L and X and sigma.
Okay, so formula is actually clear. So if I take small l equal to capital L,
Yes.
then you want to show this whole stuff goes to 0.
No, why? No. I'm not wedded to the infinite width limit. I just want to know how things change. And the way I think about it is, you thought you were close to Gaussianity, and so you say, okay, let me compute the first order correction, and just understand what happens with depth. And you see that actually the first order correction, exactly as you say, starts to become order 1. It's no longer a correction at all.
So we will not end up on
No, that's the point. Just like in the random matrix thing, you go, as soon as L over n is positive, you're just not actually close to the free probability world at all, or the Gaussian process world. It's just, but you kind of see it coming out. You see the mechanism by which it happens. That's the, yeah. Oh, excellent, I'm doing well. Maybe Giovanni will disagree. Okay, very good. So let me show you how a calculation like this works. And okay, just like in the Gaussian process derivation, I'm going to do it modulo the hard theorem, which I'm not going to tell you how to prove, but I'll show you what the idea is as it goes. Okay, so all right. So recall what we had before. Recall that at finite width, when you have zl plus 1 I of x, it wasn't Gaussian, but it was Gaussian conditional on the previous layer. That was like the basic structure we were using. Okay, and all but Lucia are not brave enough to try to do the non-Gaussian case. So good luck. Where's Lucia? There she is. Okay, so what do we know? We know that this was Gaussian, mean 0, but with a random variance, KL hat. I think I called it L plus 1 of XX. That was right, my notation before. I'm probably going to drop the x's fairly soon. Where KL plus 1 of XX was this thing. It was CW over NL, the sum on, maybe I should use J. J goes from 1 up to NL of sigma of ZLJ of X squared. This is one of these collective observables. This is what we had. Okay, so fine. So you're not Gaussian, but you're conditionally Gaussian. And the point is that this is a random object, right? The neurons in the previous layer are fluctuating, so unless you take the width to infinity, this is just what it is. But the basic kind of thing I'm going to use is the following. So sorry, let me extend this notation. Fine, let me do it this way. Call that, and then I'll say note that, just to connect the notation from one to the other. This GL is nothing more than the expectation of K hat L, right? So GL is the expectation of K hat L. I'm going to drop the x's if you don't mind. Just don't have to write XX every time. Okay, so let me write, as a result, let me just this suggests defining, let's write KL as its mean plus a fluctuation. So I'm going to define delta L plus the expectation of K hat L. So this delta is just the difference between K and its mean. This is natural to do, right? Because we said that these converge to their mean. So the fluctuations are small, i.e. this delta is small. And the theorem, whose proof I won't tell you, but I'm just going to recall it for you, is the following kind of thing, that if you take the expectation of the powers of these fluctuations, right? So delta is one of these centered collective observables. It's an average of some function applied to every neuron at the layer minus its mean. So that's legitimate. This scaled like O of n to the minus q over 2, where, okay, n is my generic notation for the NLs. So these are all small. Okay, so this is the thing I need to remind you from before. And now I can do the derivation, and I promise it's not going to be too terrible. Depends on your definition of too terrible. Okay, so step one is to realize that this fourth cumulant that I'm interested in studying is easy to write down in terms of delta. It's not completely obvious, but it'll be obvious right now. So you have KL plus 1, 4 of x. I'm just reminding you of the definition is 1/3 the expectation of ZL plus 1 I of x to the fourth minus the expectation of ZL I of x squared. Right? And now let's just compute this expectation, but just integrate out only the weights in layer L plus 1. Right? We know that, so condition on this kernel of all the things at layer L, and let's just do the Gaussian integral that come from the weights in layer L plus 1. Well, the expectation of the fourth power will just be 3 times the variance squared. Okay? And this thing, sorry, what did I do? Thank you. Okay, I was going to say, nothing works. Okay, and this is minus 3 times the variance squared. Okay, so this is going to be exactly, the 1/3 will cancel. I'll have the expectation of K hat L plus 1. So I have 3 times the expectation of this squared minus 3 times the expectation of K hat L plus 1 squared. Like this. Okay, so all the 3's cancel. Got it right? And you just get the variance of KL, which is delta. Okay, so this is just, if you want, the expectation of delta L squared. No. Wait. Let me change the notation. I just want this L to match which layer I'm averaging over. Okay, otherwise it's really awkward. So you're right, except that you're wrong, and I don't know what you're talking about. Okay, there we go. Sorry. Okay, thank you. Yes, I don't even know who said that, but that's right. Okay, so in the end, all we have to do, this thing is a mean zero random variable. We just have to study the variance of delta L. So the fourth cumulant is just the variance of the conditional variance, if you want to put it that way. Okay, that's kind of step number 1. Okay, step number 2 is not to be afraid, which is difficult, but we can do, and to actually do some calculation. So I need a bit more board space, so I'm going to take this up. I'm going to put this down. I'm going to start doing the calculation here. And we're going to do it. We're going to it's much easier than it seems once you know that kind of theorem that I'm black boxing for us. But I think it's like a good lesson about how to do almost Gaussian integrals, which is never to panic and just go to momentum space. Okay, so very good. So now what am I supposed to do? So I claim the right thing to do is to start by deriving this recursive formula that I claimed for the expectation of f. We're ready to do it. It'll take me maybe 2 boards. Not too bad. So you fix some function f, and you ask, what's the expectation of ZLI of x for I goes from 1 up to m? Okay, so you say, how in the world are you going to do this? And I say, easy. Very easy. Step number 1, because things are conditionally Gaussian, it's always easier to do Gaussian integrals in momentum space. So you take the Fourier transform of f. So xi is my dual variable. Okay, I have one dual variable for each one of these. I goes from 1 up to m. And I just have to integrate against the characteristic function of the z's. Okay, so I have to integrate against the expectation of exp of minus I, the sum on m, say j. J goes from 1 up to m of xij times zl plus 1 j of x dxi. Okay, this is like I won't write the Rm anymore. That's an m-dimensional integral. Okay, so now what's the point? So again, I just want to exploit as much as I can the fact that ZL plus 1 is conditionally Gaussian. So I'm going to integrate out the previous layer only. So this is a full expectation over all the weights. But let me just do part of this Gaussian integral that come from the weights in layer L plus 1. So I'm not going to freak out too much and just write it down. So you still have the expectation over all the previous weights, but the Gaussian integral part is easy to do. Right? Each of these just gives me a minus 1/2 times k hat L. Okay, and you just get the sum of the squares of the x's. So you get minus 1/2, you get the norm of c squared, and you get k hat L. I'm dropping the x's. That's it. I'm done with the x's. I've decided I'm dropping them. Okay, so this is like the basic starting point for the formula. And you say, okay, great, now you're stuck. You did the easy part of the integral. What about the hard part of the integral? And I say, what hard part of the integral? I don't see anything hard. So what do I know? I know that this k hat is very close to its mean. So let me use the fact that it's close to its mean by adding and subtracting the mean. So which I called g, if you recall. This is f hat of xi. Now you get exp of minus 1/2 xi squared, because that's deterministic, times gl, okay, times you get the expectation of exp of minus 1/2 xi squared times delta L dxi. Okay, you'll say, well, great, you changed one random variable for another random variable. Why is that good? But the whole point is that the deltas are small, right? That's this theorem that I black boxed for you. So what I'm now going to do is I'm going to Taylor expand this thing. Integral. So this is where I'm cheating a little bit. You have to check some convergence issues, but everything is okay. So maybe let me say, GL. If you just ignore this part down here, this just says the Gaussian integral of f against the Gaussian with covariance g with all IID neurons. Okay, so that's like the kind of basic integrals you get. But you have this extra term which complicates your integrals a little bit. So we have to expand it. Okay, so you get the expectation, and I just literally Taylor expand the exponential. The sum on q greater than or equal to 0, minus 1 to the q, 2 to the q over q factorial. This is the minus 1/2. Then I get c to the 2q, and I get delta L to the q dxc. That's just what it is. And now you can see, I'm going to erase this in a moment, why it's so nice to have that estimate on the deltas. Right? Because I know now, which is what a physicist would claim is trivial, but I claim is not trivial, but okay, difference of opinion, that this power series is actually as nice as you like, really. Okay, you have an exponentially decaying term in the psi variable, no problem with integrability out in front. And then these things are all polynomially small in n. That's great. It's like a dream come true, or maybe a nightmare. It's hard to say. So I'm just going to keep the terms corresponding to q equals 0, 1, and 2, and then drop all the higher order terms, because all the higher order terms, by my estimate, give me O of n to the minus 2 corrections. Okay, so what do I get? I get the integral of f hat of xi. I get exp of minus 1/2 of xi squared times gl. Very good. And then I have some stuff. Okay, I just have to Taylor expand. So, okay, when q equals 1, I get 1. Good. That's what I should be getting. Okay, plus, when q equals 1, okay, just to see if anyone in the world is following, what do I get when q equals 1? Scary to ask that question, I know. 0. Okay, wow, you can't fool Yvonne, right? Q delta is a mean zero random variable. That's the point, so that's good. And then when Q equals 2, I get the expectation of delta squared, which was kappa L, right? So I get kappa L plus 1 4 over 8. And then I have the norm of psi to the 4th. And that is it, plus O of n to the minus 2 dx. Ho ho! Look at that. Not too bad. Now I declare victory. I'm done, right? Why? Remember, polynomials on the momentum side just correspond to derivatives on the original kind of physical side. Okay, so this is precisely, this 1 gives me the expectation with respect to the finite width Gaussian. That's what I wanted. F hat, or not F hat, sorry, of F. Plus I get my correction term with the 8 and everything. It's amazing, right? And the norm squared of Xi is like the Laplacian in the Z variables, and I have to square the Laplacian. So I get the expectation with respect to GL of the sum on J goes from 1 up to M, second derivative with respect to the jth thing squared applied to F, plus higher order terms. Okay, so that was nice. It's almost as if I optimized the derivation. Oh God. Okay, trust me, the first time I did it, it wasn't this nice. Okay, so very good. And now let me complete the proof. Now we're basically already there, I claim. So we now want a recursion for kappa. But notice that our formula for kappa that we have from step 1 says that the fourth cumulant in layer L plus 1 is something about layer L. Okay, very good. So now I just say, well, so this is step 3. I don't know if I wrote step 2. Was I smart? Nope. Okay, but this is step 3 nonetheless. Right, so you say, well, kappa L plus 1 4 of x is the expectation of delta in the previous layer squared. Okay, very nice. So I'm about to apply this formula I just derived in the previous layer. My life's going to be good. And what am I supposed to get? Well, okay, so this is going to be the expectation. Let me just give this stuff a name. So it's going to be CW over NL. The sum on I goes from 1 up to NL. And you're going to have, I'll call these x sub I squared, where I'm just writing, to save myself a little bit of notation, this is sigma of ZLI of x squared minus the expectation of sigma of ZLI of x squared. Okay, I'm just writing in the definition of what delta is. And okay, it's not too bad. When you expand this out, you're only going to have 2 kinds of terms just by symmetry. You'll have a term where after you square the sum, where both indices are the same, and when the 2 indices are different. Okay, fine, easy. So you're going to have CW squared over NL, and you're going to have the expectation of x1 squared. That's when the 2 terms were the same, but it's got a prefactor of 1 over n, and this thing is going to correspond to the first term in our recursion. Okay, you can literally see it already, essentially. Plus, you're going to have CW squared, and you're going to have 1 minus 1 over NL. That's the proportion of terms that are different, times the expectation of x1, x2. That's what you're going to have. And then you're just going to plug in this formula here. Okay, this is a function that depends on 2 variables, 2 of the neurons. This function only depends on 1 of the neurons. So my formula is perfectly valid. I apply it for m equals 1 and m equals 2. And I promise with a little bit of algebra, you get the recursion. Okay, that's the whole derivation that I wanted to present. Okay, very good. So let me just stop for a second and ask if there are questions or comments about this. I know it can be a little brutal to see, but I at least wanted to show you that it's like, you can present it on the board with like some level of care and it's not insane. Yeah. Does not depend on L? No, it's not clear. In fact, for some nonlinearities, there's no choice of CW that will guarantee this. But those things correspond to networks that you can't train in practice. There's no initialization that gives you numerically stable kind of, so people don't use them.
Why your ratio is not dependent on L?
Right. So the way to think about it is, let me just start in the simplest case. Like you have this KL of XX thing, and just think of it as a one-dimensional dynamical system. What you basically ask is that it has a critical fixed point. Like there's some K star that the KLs converge to, and you ask that the convergence is not exponential. That's what the CW does. So some nonlinearities don't have a fixed point at all, and like it just diverges or whatever. But for the nonlinearities like ReLU or Tanch or whatever, they have finite kind of fixed points. And you just need to tune the CW so that you don't converge too quickly. But it's not obvious. You have to check. And then it's even less obvious when you have more than one input, what happens. And you have to do some more analysis. And for some nonlinearities, again, you can do it, and for some you can't. But again, I'm not really presenting it this way, but being able to tune to criticality is basically necessary for having a network that's trainable. Otherwise, your gradients and values have really bizarre properties. You can't train at large depth. So, yeah.
Comment, the procedure that we are doing is like applying the sign solution to the sign equation. I mean, you can handle more stuff than just the cumulant. You can, I think, with the same procedure, you should be able to handle any function when you apply the sign solution to the sign equation. You can go all the way from step with a different function. But cumulants, you can handle.
Well, yeah, so you're right, but notice that in the statement of the theorem, I handle a general function, the general f. You see what I mean? So it's kind of like, you're right in the sense that what I learned when I tried to do the cumulants is that you can't do the cumulants by themselves. In order to do the cumulants, you're just forced to do general functions. And so, and then you specialize to the cumulants to get the recursion, but like, yeah, indeed. But notice maybe that the main object that tells you what happens away from the Gaussian kind of calculation for a general function is the fourth cumulant. That's why it's interesting to write down a recursion specifically for the fourth cumulant. Yeah.
And one actual question is more or less the same question as Gamba with the loan that you have over there. Could you get like not explicit O, but the dependence of O of n minus 2 in terms of L? So
yes, the short answer is you can. I even did it at some point in my life. And what you get is what you think you should get, which is you get L over n quantity squared plus O of n to the minus 3. So it's like, congratulations, you lost a day of your life. And like, it's kind of the same, but a little bit nicer, and nobody will tell the difference except for Arturo. Okay.
It's not obvious though, that because you could have technically L.
No, it's not obvious at all, but that's how it, I didn't really emphasize it this way, but just like in the random matrix theory story, there's a conjecture, which hasn't been proved, which in general, everything depends only on L over n. Not 100% clear that it's going to be true, but like in some situations, people have proved it now for neural networks. In some cases, they can't, and okay, it doesn't matter. If you're interested, you should talk to me about it, because there's a bit more to say than what I'm really conveying.
Just a probability, probably elementary probability question.
Yes.
This first step, so you can write the expectation of a function of a bunch of random variables as the integral of the Fourier transform. Is this like a?
Sorry, I should have reminded you of this. So in general, if you have an integral over Rk of f of x times g of x dx. So this is my f. This is the density or measure of my random variable. The Fourier transform is an isometry on Lk. So it's f hat of xi, g hat of xi, dxi. And this is just a characteristic function of your random variable. When
this result is true for anything here, you're just...
I'm not using anything there. It's just a starting point to get me going.
So, but the first step is true for everything. After that, you use the Gaussian. So I mean,
yes, correct. Correct. The first equality depends on nothing. It's almost always easier to do Gaussian integrals after taking the Fourier transform, because normally the kernel has an inverse and there's a determinant, and it's like good luck to you. That's my feeling. But here there's no inverse and there's no determinant. It's all kind of in the exponent, and okay, things are So this was just a way to make the calculation look easier. But the first step is always correct, indeed. Okay, very good. So let me say, because I only have a couple minutes left. Sorry, I have to choose what to say. Okay, so let me do this. So here's an important correction. Not correction, but like amplification of what I'm saying. So suppose for just 1 minute that sigma of t is the identity. Okay, you're in this deep linear case. And recall that k L plus 1 of xx prime was CW times the expectation with respect to KL of sigma of ZL1 of x, sigma ZL1 of x prime. That was the recursion we had for the kernel. So when sigma is the identity, the sigma is gone, and you just immediately get, when sigma is the identity, CW times KL of xx prime. Right? This is literally speaking, you have a Gaussian, in fact, a two-dimensional Gaussian vector evaluated x and x prime, and you're just literally computing the expectation of the product of the two components, so the covariance between them because they're centered. Okay, so the simplest version of taking CW to be something nice, okay, to kind of answer Yvonne's point, is for linear things, you take CW equals 1. Otherwise, it's going to either exponentially go to infinity or converge to 0. That's kind of the only sensible thing to do. Okay, very nice. So that's what happens for linear networks. But now let me take for one moment sigma of t is equal to the ReLU. Obviously kind of an interesting case. And for the ReLU, things are a little bit complicated. Well, not complicated, they're just a little subtle. Okay, so I'll leave it to you just so that I don't run over time. But it's an easy calculation, very much in the spirit of this thing, to show that on the diagonal, if all you care about is the value at a single x, when x prime equals x, you just get CW over 2 times KL of xx. Okay, so if you want the variance in input not to go to infinity or to go to 0 exponentially, your only choice for CW is CW equals 2. And indeed, this is what people always do in practice. People have known this for other reasons. You have to take CW equals 2 for ReLU. That's what tuning to criticality looks like. However, the following is also true. If you if you take two different inputs, x and x prime. So let me just assume. Let me not assume anything. I assume nothing. Okay. So if you ask what happens at large L for the covariance kernel between two different inputs, here's what happens. So you get the variance of one of them, the variance of the other one, okay, with the square root, of course. This is the normalization, times, 1 minus, believe it or not, 8 over 3, wait, what number did I get here? Wait for it. 3 pi over 8 times L to the minus second power, okay, plus O of L to the minus third power. This is how things look. I'm not saying it's obvious. I'm just saying to look at what the formula is telling you. So what it tells you is that even if you set it up so that the variance is constant, which sounds great, the covariance between any two inputs gets closer and closer and closer and closer to 1, or more precisely the correlation, right? If I divide the covariance between the square root of the product of the variances, this is the correlation. Any two inputs get closer and closer and closer and closer and closer together. And this is just a fact of life. This is if you want an ergodic theorem for nonlinear dynamical systems, any two different initial conditions go to the same output. And so what this tells you is that if you just wanted to study large depth networks, it's not a good idea to take a nonlinearity. You have to do something that is somewhere between linear and nonlinear if you want to have a hope of having a non-degenerate two-point function or covariance function. Okay, so the thing to do is to reshape your nonlinearity. So sigma of t should be like t plus. Okay, let me give you one example of what you can do, but there are other examples. Take 1 over the depth times t cubed. In fact, let me give myself a constant here, psi over the depth. Psi is just an order 1 number. Okay, so this is an example of a shaped nonlinearity, as it's called. Shaped activation. And it might seem kind of funny, but the point is that if you're the identity, taking large L is perfectly sensible, no problem. if you're any nonlinearity, truly nonlinear, it turns out that you get some kind of degeneracy like this. You just can't take a large depth limit and get something that looks nice. So what you have to do is in every layer you need to be close to the identity. And I'm telling you, you should be this close to the identity. So in every layer you're close to the identity, but over L layers you're order 1 distance away from the identity. Okay, so if you're really interested in studying just these fully connected neural networks at large depth, you have to take shaped activations. So it can look like this if you have odd functions, and it can look like this, square root of L times ReLU of T, if you want these kind of ReLU type functions. Okay, they're slightly different scalings. Don't ask me to explain why. I'm just saying conceptually the thing to do is to make your nonlinearity close to the identity in every layer. That's just what you have to do. And then all of these theorems start to kind of, these theorems work for any nonlinearity you want. But for this reason, you get funny answers sometimes when you take L to infinity and you have more than one input. Okay, so that's just to be totally transparent. So I know I'm already 1 minute over. So let me stop here, and then I'm going to take questions. Okay, I think that's the thing to do. Yeah, please.
So I try to understand the moral of this course.
Yes.
I was expecting in the beginning that capital L will be of order n, but that's not the case, right?
So right.
Here, my interpretation is saying.
Well, it is, but you should think of it as a small. It's like you treat L over n as a perturbative parameter. You're perturbing around L over n equals 0. So it's like you get corrections on the order of L over n, and then the next order term is like L over n quantity squared. You know, so if, yeah, so but like what if L is 0.1 times n? You know, like I'm just saying, like if like L is epsilon times n. That's the way to think about it.
And then you have shown, I mean, basically you have shown how far away you are from analysis.
Yes. Also from being a linear model. I haven't shown you that side of it, but yeah. It controls everything. Like how far you are from the NTK regime. I didn't show you that, but like, okay.
And so what does it tell you? Tell you, like, what's the moral? The moral is if L is not too big, then you're not so far away from your usual linear.
Yes.
That's it.
So it really said, look, in practice you want more and more parameters in your model. You know, like you just want to increase the number of parameters, the number of data points grows. And you might have been worried that as you increase the number of parameters, the width, you get closer and closer to a linear model. It sounds bad. This is giving you a prescription that as you increase the width, you should also increase the depth. That's basically what it's saying. That's the point 1. Point number 2, it's giving a prediction, which, okay, the theorems don't directly imply, but they suggest that if you double the width and double the depth, you'll have roughly a similar network. That there's really some scaling limit where you send n and L to infinity together at a fixed ratio. And if you want to be close to some limiting model, you should think about scaling both of them together. That like gives a prediction. And okay, that's indeed true, at least if you have these rescaled nonlinearities so that large L doesn't like, cause numerical instabilities in training. But it's not implied by this theorem directly. It just suggested. You know, like this theorem here, I presented it for the cumulants, roughly. It turns out it's also true for things like the gradients of your model and the Hessian of your model. You know, how close are you to your linearization? You can do perturbation theory for the whole trajectory of training around the NTK limit. You can at least do it in a physics level of rigor. That's what I've done before.
But the really kind of interesting case would be L equals n.
So yes, that's what. So in order to understand L equals n, that's a non-perturbative correction, as you see, because every 1 over n power comes with a corresponding L in the top. And so resumming these corrections is not something we know how to do in general. It's just, even in the random matrix theory thing, you know, where you just have like no nonlinearity at all, and I ask you, what are the statistics, what are the microscopic statistics of the singular values? It's an open question in general. You know, like we don't even know how to do it for that. It's like just hard. And we think it's only L over n that matters, but like other than integrable examples like products of IID complex Gaussians, we don't know.
Probably the cumulants are not the right tool. So in that case, like, for instance,
Oh yes.
the normal is not determined by the limits.
So, right, the cumulants are not the right tool because you need to keep track of all of them. That's kind of the moral of the story if L over n is. That's right. Although really the right thing to do is like the linear example suggests, take the log and then you're Gaussian. No, but like I don't mean that in a totally joking way. Yeah. So what I would say is like this suggests that like in the usual non-parametric statistics world where you should take n and d to infinity together, that's the right kind of high dimensional thing to do. There's another parameter here which is L. So you should take n and d and L to infinity together, and you should study what happens. And fixing L will lose out a lot of information, if you're not careful about it. That's kind of the moral of it. So I'm not telling you about follow-up works, but like I've done Bayesian inference with these nonlinear neural networks when the depth and the width and the number of trained data points all grow, and you can start saying things about how you make predictions after training, blah, 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 training by Bayesian inference. So it's like the starting point for understanding various forms of training. If you can't understand this, no form of training is really kind of accessible to you. But it's just the starting point, indeed. So the moral is more work to be done. Excellent. Yes, please.
I might have missed it, but if we would insist on the ReLU without the E plus,
Yeah.
If we would insist on that, and you said that something funny happened with the limit, which is what? Sorry.
So I'm saying if you just stare at this equation, you notice that if you take this and divide by this, you get the correlation between any two neurons, between the value of any neurons at two different inputs. And the correlation converges to 1. So in other words, any two different inputs give you, up to scale, the same random output. And your neural network's totally degenerate and untrainable as a result. Because every input gets mapped to the same output. I mean, there's no training to be done once you've mapped to the constant function. There's kind of, so this lists the numerical issues or mathematical issues at infinite depth. So yeah.
So interesting.
Yeah, I'm just saying this is a limit where the probability distribution you get at infinite depth is like very degenerate. You get something horrible. And so you just shouldn't study this limit. And to slow down the speed of convergence basically to stationarity of your Markov chain, you have to slow it down by rescaling the nonlinearity. That's kind of how it works. Yeah. Oh, yes.
Would it be feasible to achieve that by using the leaky ReLU where the slope of the left branch would be learned from the trained?
Well, the short answer is this is functionally what this does. Right? I mean, this looks like a leaky ReLU if you just rewrite it a little bit. Right? Because but the point is you need to make it close to the identity. You see there's an L here. Your L is supposed to be large in this story. So it's like if you want the total network to do something that has like an order 1 difference from where you started, right? So the linear network exactly preserves where you started. You need to have a small difference in every layer because you have a large number of layers.
And to formalize this funny symbol, what would be an example of that tilde L in the numerator?
So tilde?
The sigma of t is t plus this.
Yeah, so for example, this one.
Yeah.
So.
In the numerator, the straight.
Oh, that's a constant. That's psi.
Sorry.
Just take psi to be 1. Yeah. I'm just saying to control your nonlinearity, you could just control this constant. That turns out to be a sensible thing to do. But I'm not saying anything beyond that. Yeah. Great.
Thank you.